Hey guys, I am coming at you from the car, and today we're talking about vectors. And I don't know if you remember this little guy from Despicable Me, but he was one of the enemies, or I don't know what you would call it. He was a villain. His name was Vector, and he talked about magnitude and direction, right? So we're going to be talking about that today. So let's jump in. Before we get started on all of our vocabulary, I just want to go ahead and get started on introduction for section 1. So let's go get started on that first blank. So a directed line segment, we call this vector PQ, has an initial point, P, and a terminal point, Q. So that's kind of like, if this is my initial point P and my terminal point Q, it can only go in this direction. The magnitude is another word for the length. Okay, so when Vector said magnitude, he was talking about the length, how long something is. Of the directed line segment, PQ is denoted by, and we use the notation that looks like this. It looks like a kind of a double absolute value, and whatever it is that we're trying to describe that we want the length of is going to go inside of that. Okay, and it can be found by basically using the distance formula. Okay, so remember, length and distance are the same idea. When we're talking about vectors, we use the word magnitude. So let's talk about what the component form of a vector is. So component form is a vector whose initial point is at the origin 0, 0. This is otherwise known as standard position, can be uniquely represented by the coordinates of its terminal point, whatever its x quote-unquote value is and its y value is. This is called the component form of vector V. And when we say vector V, when we handwrite it, we use the letter V with the vector notation on top. If we're typing this, it would just be a bolded letter. Written like this, where this bolded V or vector V is component form, it has these kind of angled parentheses, okay? That tells you that it's a vector, not just a point on the plane, where V1 and V2 are the components of vector V. And the component form of the vector with the initial points, remember, initial point is P, where the P is the point P1, P2, and the terminal point Q, that's our ending point, is the point Q1, Q2, is written like this. So this is for the component form. So to find the component form, we take Q1, which is the ending point of the x value, minus P1, which is the initial point of the x value, comma, and then Q2 minus P2. And we're going to close that with that angled component form parentheses. And we say that that is V1, comma, V2 equals vector V. This is bolded in type, and if we were to handwrite that, we would write it like this. So the magnitude or length, and we know that because it looks like that double, like absolute value, but we know the magnitude is just our distance formula. So Q1 minus P1 squared plus Q2 minus P2 squared, which is going to be the value of the component form of the vector V1 squared plus the component form of the vector V2 squared. So let's kind of talk about what that really looks like. So it says find the component form and the magnitude of the vector that has its initial point 1, 7 and terminal point 4, 3. So remember, we know that initial point is P1, P2, and the ending point is Q1, Q2. So here's what that looks like. we're going to say vector v equals the component form is going to be, just like up here, q1 minus p1. So we're going to say q1 minus p1, so the x values, comma, q2 minus p2, which simplifies right here. 4 minus 1 is just 3, and 3 minus 7 is negative 4. So that's the component form of the vector starting at 0, 0. And it would look something like this. So if I'm starting at 0, 0, it would go over 3, down 4. So this is the vector and what it would look like. Okay, that's vector v. And then if I wanted to find the magnitude of vector v, we're going to take that. It's basically the distance formula. So the square root of, and since we already found q1 minus p1 and q2 minus p2, which is here and here, we can just take the component form, so that's 3, and square it, plus negative 4 and square it. And we end up with the square root of 9 plus 16, which is 5. Okay, so geometrically, the product of a vector and a scalar just means to multiply by a coefficient. And we call that scalar k. Okay, and we say that the vector that is absolute value k times as long as v. So a scalar, multiplying a vector by a scalar, is like doubling it, tripling it, whatever that k value is that's going to multiply. It's going to go in the same direction, but the magnitude will get k times longer than it was. So if k was positive, then the vector has the same direction. But if k was negative, then the vector is going to actually reverse, and it's going to go in the opposite direction. Okay? So the way that we would add two vectors u and v geometrically is we're going to first position them without changing their lengths so that the terminal point of the first vector coincides with the initial point of the second vector. So if you're like, what in the world does that look like? It looks like this. So let's say I've got two vectors. I've got vector, we'll call this vector u. And if I wanted to know how to add it to vector v, I'm going to stick vector v, instead of having it start at 0, 0, I'm going to stick it right on that ending point of u. So let's say this is vector v. Then my total result would be as if I started here and I ended here. And that's that resultant u plus v. Okay. And this technique is called the parallelogram law for vector addition, because the vector u plus v is often called the resultant and is the diagonal of the parallelogram that has u and v as its adjacent sides. Okay, so I can kind of show you what that means if I was talking about if I was talking about what that would look like. So I could show you that this would be like a parallelogram here where the resultant vector is right in that middle. So that's that parallelogram idea. Okay, so let's go ahead and go to the next part. It says let vector u, which is component form u1, u2, and vector v, component form v1, v2, becomes, let them be vectors, and let k be a scalar or real number. That the sum of vectors u and v is the vector u plus v such that the vector form of u1 plus v1, comma, u2 plus v2. And the scalar multiple of k times vector u, which would look like this, would equal the vector of whatever k is times u1, comma, k times u2. That's your vector form. So for example, if vector u was 1, comma 6 and vector v is negative 4, comma 2 in component form, if I was going to find 3u, 3 vector u would be 3 times vector u, which is 1, comma 6. So that would be in component form 3 times 1, comma 3 times 6, which is just 3, comma 18. In vector form, so remember, everything in vector form starts at 0, 0. We would go over 3 and up 18. So that would be that scalar 3u. It's in the same direction as just u. And then for part B, if I wanted to find vector u plus vector v, I'm going to say vector u, well that's 1 plus negative 4, comma 6 plus 2. And then we simplify that, we get negative 3, comma 8. So the addition of vector u and vector v is just negative 3, comma 8. So let me show you what that would kind of look like if I was adding it. So if I've got my vector u, which was originally component form 1, comma 6, so that would be starting at 0, 0, vector u, and then going over 1 and up 6. Okay, so that's my vector u. Now vector v is negative 4, comma 2, so when we add them, we put them tail to initial or ending terminal to initial, and we're going to go to the negative 4. So we go over negative 1, 2, 3, 4, and then up 2. Okay, so this is our vector v. So if I'm adding them in total from starting to the very end, this is our vector, which is u plus v. And let's look, we just said our vector should be negative 3, comma 8, and look at that, negative 3, up 1, 2, 3, 4, 5, 6, 7, 8. And there it is. All right, let's fill in our vocabulary really quick. Now we kind of have an idea of what we're talking about here. Okay, so remember a vector is actually all directed line segments that are equivalent to the same length and direction. So for example, if I were to draw this vector here and call this vector v, it's going to be the same as another vector. So I'm just going to show you what it would look like. This same exact one right here. Okay, I'm going to kind of erase this a little bit. There we go. And it would be the same vector as this one here. Okay, so we could continue to duplicate the same length and the same direction everywhere, but all of those are vector v, and it doesn't really matter where it starts. So standard position, remember the standard position always starts at the origin, 0, 0. If it's a 0 vector, basically the starting and ending point line at 0, or initial and terminal point, are at 0, 0. So therefore we have this bolded 0 vector, which is the component form 0, 0. A unit vector is the vector v such that the magnitude of v equals a distance of 1. Standard unit vectors, that just means if something is, the standard vectors are 1, 0. Think about what that looks like. It would look something like this if this was our 1, 0. This unit vector would look like this, where this was a 1. Okay, so that's our standard unit vector, 1, 0. And I would have another one, 0, 1, which would look like this, starting at 0, 0, going up 1. Those are those two standard unit vectors. So we call this first one vector I, really bold, and we call this one J. So this is like the horizontal vector component, and this is the vertical. And this is so we can break up any vector into two separate vectors, okay? So that we can break up any vector into just terms of just a horizontal component and just a vertical component. And then the direction angle is the angle measured counterclockwise that a unit vector makes with the positive x-axis. So that the vector makes with the positive x-axis. All right. Thanks for taking your notes. Thanks for being awesome. Bye.